All right, let's get into a fantastic bit of cosmic detective work. This is a story about a scientific puzzle that had astronomers scratching their heads for more than 20 years, until a breakthrough finally cracked the case. We're talking about the Pulsar puzzle.
So imagine you're an astronomer, and you're looking at these incredible cosmic clocks called pulsars. They're supposed to be some of the most reliable timekeepers in the entire universe. But for decades, there was this one group, and they just seemed broken. Their timing was all wrong.
But here's the twist. What if the clocks weren't broken at all? What if the problem wasn't millions of light years away in deep space, but right here, in how we were reading the data? That's the huge question at the heart of this whole thing. To really get what's going on, we have to start where the mystery began. Let's open the case file on this cosmic anomaly.
Okay, so our main suspects are a group of about 50 pulsars. Back in 1988, astronomers called them the partial cones, and a key member of this family is a pulsar named B1240-64. It's way out there, 7,000 light-years away. And get this, it's so important that it was actually included on the Voyager Golden Record as part of a map for any alien civilization to find planet Earth. But its signal, which should have been neat and tidy, just looked weird, distorted, and lopsided. And this wasn't just some minor little problem. Check out this quote from the original paper that named them. These weird signals were so confusing, they made scientists question their entire theory of how pulsars work. They were literally asking, is our whole model wrong? That's a huge deal.
So what was this big, important model that these pulsars seemed to be breaking? Well, let's talk about the standard theory, the lighthouse in the stars.
For a long time, the go-to theory has been what's called the core/cone model. It basically says that a pulsar's radio beam is this beautiful, perfectly ordered structure. You've got a central core of energy, and then it's surrounded by one or two nested cones of energy, all perfectly symmetrical.
The best way to picture this is to think of a lighthouse. A pulsar spins around, and its beam of radio waves sweeps across the cosmos. According to the model, that beam is perfectly shaped, so every single time that beam flashes past Earth, we should see a clean, predictable, and totally symmetrical pulse. Simple, right?
Well, not so much for our partial cones. Their signals looked like the lighthouse beam was all warped and patchy, almost like huge chunks of the light bulb were just missing. They were totally asymmetrical and incomplete, and they flew right in the face of that neat core/cone model.
And that's where the puzzle sat for 2 decades. But then, new technology came along and gave astronomers a totally new set of eyes, letting them gather fresh clues and finally build a case for what was really going on.
The big difference was the technology. The old way of looking at these things, average polarimetry, was like taking a long exposure photo of a spinning wheel. Everything just blurs together. But the new method, single pulse polarimetry, is like using a super high-speed camera. It can capture every single pulse, crystal clear, revealing details that were completely hidden before.
And what they did with this new tech was just brilliant. Instead of averaging everything together, they started hunting for these rare, super bright flares of energy that would sometimes pop up on the very edges of the signal. And by taking only those rare, bright flashes and averaging them together, a hidden pattern just jumped out. All of a sudden, this messy, distorted signal revealed a beautiful, whole, and perfectly symmetrical shape hiding underneath. The perfect cone was there all along. It was just usually too faint for us to see.
Okay, so that was a huge clue. The beam wasn't patchy, it was complete. But it still looked distorted. So why? Well, this is where the investigation takes a really cool relativistic plot twist.
This led scientists to ask a game-changing question. What if the pulsar's beam was actually perfect, just like the model said it should be, but something was warping the signal after it left the pulsar, twisting how it looked by the time it got to us here on Earth?
The answer lies in something called aberration and retardation effects. It sounds complicated, but it's really a consequence of Einstein's relativity. See, pulsars spin incredibly fast, and their radio signal isn't emitted from the surface, but from hundreds of kilometers above it. That combination of height and speed means the signal we see is slightly delayed, making it look like it shifted backward from where it really started. And here it is, the smoking gun. When the researchers looked at the new data, they saw a consistent pattern. For 19 of the 23 pulsars they studied, the true center of the signal was consistently lagging behind the brightest part of the pulse. The systematic delay, that was the classic signature of these ASR effects in action.
Now, using this time lag,
The scientists could calculate the exact height where the radio waves were being emitted. And the answer? About 300 to 400 kilometers above the pulsar's surface. Now here's the kicker. That's not some weird exotic number. That's a completely normal emission height for any pulsar. This was the strongest proof yet that these guys weren't oddballs at all.
And with that final crucial piece in place, the whole mystery just snapped into focus. Let's look at how the pattern was finally revealed.
This table just sums it all up perfectly. The old way of thinking was that these partial cones had physically broken, patchy beams, which made them cosmic weirdos that didn't fit the rules. But the new interpretation, with way better data, shows their beams are perfectly normal. It's just that the signal gets distorted on its way to us, making them perfectly orderly pulsars just in disguise.
The moment the researchers corrected their data for these relativistic distortions, all the partial cones fell right into line. When they plotted the results, they landed on the same neat parallel tracks as every other normal pulsar out there. They fit the core cone model perfectly. The case was closed.
So, the grand finale, the big punchline to this whole 20-year scientific mystery, is that the cosmic oddballs were never actually odd at all. They were just misunderstood. And that leaves you with a pretty amazing final thought, right? This entire cosmic puzzle wasn't about broken objects in space. It was about our own limited point of view. It was solved simply by finding a new way to see. Which really makes you wonder, what other illusions are out there in the universe, just waiting for us to look at them in a new light?